Welcome to AI Evaluation. Something major is happening at Google. In just a few days, they unveiled 3 groundbreaking AI innovations, each targeting a different domain, but all with one overarching aim: making humans obsolete in advanced tasks. We're talking about writing in-depth research papers, creating machine learning pipelines, and even mapping the entire Earth like a virtual satellite. Let's start with the first innovation: TTDDR, or Test Time Diffusion Deep Researcher. The name might sound like a bit of a puzzle, but what it does is a major leap in making AI behave like an actual human researcher. See, most AI agents that generate research reports are just a bunch of tools duct-taped together. They don't think like us. Real researchers don't just spit out results. We plan, search, refine, draft, rewrite, gather feedback, and then reshape everything until it feels solid. TTDR mimics that process. It treats the whole research journey as a kind of diffusion process, like slowly cleaning up a blurry image until the final version becomes crystal clear. Only here it starts with a rough research draft, and that draft keeps evolving with every step. What's clever is that it doesn't just rely on a fixed database or internal knowledge. TTDDR pulls in external info at every single stage, using a retrieval system that helps the AI improve the draft as it goes. That way, it doesn't lose track of context or fumble the flow like other agents usually do. Each draft version becomes the foundation for the next, just like we do when writing a paper. Google tested it on some seriously tough benchmarks that demand multi-step reasoning and in-depth search. Think complex research questions that can't be answered with a quick summary. And the results? It beat OpenAI's deep research system almost across the board. On long-form reports, TTDDR won nearly 3/4 of head-to-head comparisons. Even on datasets with short-form answers, it still outperformed OpenAI by close to 8% in some cases. It also ranked higher in helpfulness and comprehensiveness, especially for those multi-hop layered tasks where most agents fall apart. It runs through 3 major stages: planning, iterative search, and final report writing, each one powered by its own set of small agents and workflows that self-improve using something Google calls self-evolution. That mechanism basically lets each part of the pipeline learn from previous errors and reconfigure itself to get better. They run this in parallel, sequentially, or even in looped cycles. Now, before we move on, just to be clear, TTDR followed complex ideas more reliably, stayed focused through longer reasoning steps, and made fewer mistakes. OpenAI's system did slightly better on GIA, but across full-length research tasks, TTDR showed stronger performance overall. Now, let's talk about MLE Star. It might look like just another machine learning tool at first glance, but it's operating on a whole different level. This is a full-blown AI agent that takes a machine learning task like classification or regression and builds out real Python code that actually works and wins. The key is that it doesn't blindly guess. It starts by searching the web for relevant models, not whatever was trending in 2017, but the newest and most competitive models like Vision Transformer or Efficient Net, depending on the data type. So instead of defaulting to outdated stuff like residual network, or only using scikit-learn out of habit, it adapts to the task in front of it. But what makes MLE Star dangerous in a good way is how it refines its code. After generating a basic pipeline, it carefully tests each component to find what actually drives performance. It focuses on the most impactful part and starts refining from there. Maybe it's feature engineering. Maybe it's how the model ensemble is built. Once it finds the key piece, it zooms in on just that and iteratively experiments with different strategies, reflecting on past results. And yeah, it keeps looping that refinement until it hits gold. And when it comes to ensembles, MLE Star goes further by creating its own merging strategies instead of relying on simple voting. It proposes several candidate models, merges them using ensemble logic it creates on the fly, and then tweaks that logic based on results from earlier runs. No cookie-cutter voting. This is dynamic optimization agent style to keep things from breaking. And this is a huge problem with large language model-generated code. Google added 3 safety nets: a debugging agent to handle execution errors, a data leakage checker that scans for common security issues like accidentally using test data in training, and a data usage checker that ensures the model actually uses all the data sources provided. You'd be surprised how many models skip over JavaScript object notation files or ignore satellite imagery just because comma-separated values are easier. They tested MLE star on Kaggle tasks from a benchmark called MLE Benchlight. Out of all submissions, MLE star won medals in almost 2/3 of the competitions, and over 1/3 were gold medals. Compared to the previous best baseline, which only managed medals about 1/4 of the time, this was a massive jump. They also did deeper analysis. For example, they checked how MLE star chose models in image classification. While older agents stuck to residual network, MLE star leaned toward newer and better options without needing extra prompting. But when they did give it extra human help, like manually suggesting real multi-layer perceptron, it adapted immediately and integrated it into the training pipeline. It also proved really good at correcting hallucinated code, like cases where the large language model wrongly tried to normalize test data using its own stats. That's a no-no in machine learning, and Emily Starr caught it. Same with forgotten data. It double-checked the task description and made sure everything was pulled in and used properly. So yeah, this goes way beyond just generating code. It handles the entire process with built-in checks, smart refinement, and real flexibility. And since the code base is open source, anyone can start using it right now through Google's Agent Development Kit. Now, let's go even bigger, like planet size. This one's called Alpha Earth Foundations, or AEF, and it's DeepMind's answer to a problem we've had for decades: how to actually make sense of all the data pouring in from Earth observation satellites, climate models, drones, in-field sensors, radar scans, and more. There's just too much of it and too little label data to match. Satellites can give us images of floods or forests, but unless you have accurate ground truth labels, they're hard to use for real-world mapping. That's where AEF comes in. It's basically what they're calling a virtual satellite, an AI model that doesn't rely on waiting for the next satellite pass. Instead, it creates global geospatial layers from all the Earth observation data we have and turns them into what they call embedding fields. These fields are 10 by 10 meters in resolution, cover the entire globe, and go all the way back to 2017. Every layer acts like a high-density data tile representing climate, terrain, vegetation, infrastructure, you name it. What's wild is how compact this is. Each patch is encoded into a 64-byte vector, which is 16 times smaller than the most compact traditional models with no loss in performance. It works with past records, handles missing information without breaking, and can generate accurate maps for any date you need. If a region had clouds or missed satellite passes, AF still gives you a coherent map using learned associations and fused modalities. Under the hood, it uses the Spacime precision architecture. Basically, it processes data across 3 axes: space, time, and resolution at the same time. It combines attention mechanisms for spatial patterns, temporal layers to pull in data over time, and multi-resolution blocks that keep fine details sharp. Plus, it brings in geotagged text from Wikipedia and other sources, blending raw data with real-world semantics. This model is already in action across the globe. Agencies like the United Nations, Brazil's map Biomaz, and scientific teams are using the system to monitor forest loss, track agricultural development, follow urban sprawl, and study environmental changes that often go unnoticed, like the slow drift of sand dunes or the shrinking of wetlands. One feature that makes this possible is the ability to generate maps for any date without waiting for satellite updates. The system pulls from existing data, fills in the blanks where needed, and produces detailed, up-to-date views of regions that might otherwise be missed. There's no lag, no need to rely on cloud-free scenes, and no manual stitching together of data sets. everything is streamlined into a single, cohesive, on-demand map analysis. Instead of creating a new model for every mapping task, governments and researchers can now access AEF's global annual embedding layers directly through Google Earth Engine. This democratizes access for smaller organizations that lack large GPU clusters or extensive teams. Looking ahead, DeepMind aims to enhance this technology by scaling it to higher resolutions, incorporating more textual and local data, and evolving it into dynamic Earth twins, real-time, living digital replicas of our planet. With this in mind, what do you think is the most potentially dangerous application of these advancements? Thanks for watching AI Evaluation. Stay tuned for more insights on the latest AI breakthroughs and their impact on our world. Don't forget to like, comment, and subscribe to keep up with the future of AI.